Okay. Now, considering a length S, what we have said like this. This is the length S of the beam. The side of the section is shown here. What is given here? That is the thickness is equal to, or the width is equal to TS. Although the width is more or less same, but we have already mentioned that thickness is variable in nature. This what you see here, the thickness of the dial is allowed to vary. So the thickness of the wall is allowed to vary. So here thickness may not be same everywhere. So here what we are saying, this is the thickness here, and this is S. S is equal to 0, and this is the S. S means total length of this particular strip, total length throughout the length of the, and tau XS, this is the shear stress acting along this circumference of the beam itself. Shear stress in along X in X and S plane. Plane X is here and X is here. So this is acting in this particular plane itself. Right, X plane and pointing along X axis itself. So what we have here, this consider this by balance we have to this all this unbalanced normal force which is here, like here and here, is supposed to be balanced by this shear force tau XS distributed along the length. So what will happen? You have to add all these things and it should be equal to 0. All the forces sigma X and tau XY as well as here, and sigma X related, sigma is related, and sigma tau SS related, and you have to equate it to 0 to maintain the equilibrium itself. A tau XS into TS thickness is varying here along the less. Let us make an average thickness here into delta X. That is the thickness width of the element itself. So this is got a force here, and 0 to X, 0 to Y. Zero to S sigma STS, 0 to S sigma S XT at dx plus 0 to S sigma S T to dx into T into TS. Means this is the stress change multiplied by the thickness there, and this is and multiplied by the TS means the length of the total length of the strip. Here the thickness here at the left side and multiplied by the total length TS itself. This is the length itself. What is shown here? No, not shown. Okay. So tau XY will becomes, this portion is cancelled by here there. So tau XY will be minus 1 by TS integration of 0 to Y integration of 0 to S. This is 0 to S sigma delta sigma X by sigma X multiplied by T into delta X itself, where TS is the total all thickness as S, and observing that My is equal to 0, and the normal stress sigma X is given by this equation, sigma X I Y into Iy, Z into Yij into Mz, whereby Iyz square minus Iz Yz is. So if you divide both sides by dx, this will become d sigma x by dx, and this will become d mx by dx. Now, recalling from the elementary, what we should are supposed to recall the elementary strength of material, that rate of change of bending moment is equal to the shear stress or vertical shear stress, and we put it at minus. And substituting in, we put it here. This equation will become VST on this side. And then with this, we replace this sigma x here. Will sigma d sigma is by dx here. So what we have is this full equation. This full equation as shown here, this yis is inside the integration ring, and I square yz will be iyz. That is the polar moment of inertia, different type, or second moment of inertia. Here we have y and z, which is which can vary along the ds, along the ds itself, along the length of the strip, and is indicated from 0 to s total length. As you see, s is 0 here from at this end, and it is bent and equal to s here at this particular end. So this is 0 here, 0 here. So total length is s. So we are integrating 0 to s iy iz t into ds. Now, if we separate them and integrate iy into 0 to s y into t into ds, iyz 0 to s y into z into t into ds, and here we replace this dmz by y by dy, and it's a negative. The first integral on the right hand side is the first moment of inertia of the area between s equal to 0 and s axis, and s between the area s equal to 0 and s about z axis. You see, it is the s equal to 0 and s means along this length of the strip, and the moment of the area is t thickness multiplied by the length s, different in that distance from this area from the axis is equal to y. So it's the first moment of area along y axis, and same is the first moment of inertia about z axis itself. Now, tau xs is the complementary shear stress. Its value at any s is also given in by equation 22. This is the value of tau xs. Let qz, the first moment of the area between s equal to 0 and s and z axis, and qy, the first moment of area with the z axis. That's then. So we are replacing this integration by qz and qy, qz and qy. This equation gives us, this equation 22 here gives us the stress distribution, or this equation itself gives us the stress distribution Sx and xs. This distribution gives us the shear distribution at section x to the vertical load due to the effect of this vertical load P under the action of, under the explicit assumption that no twisting is created. So, hence, the shear stress distribution tau xy must statically equivalent to the load Vy. This means that there is no twisting is created. So this all this equation is here, the distribution is created due to the party essence of Vy. As we know that no twist is created, no other twisting is created. So the shear stress distribution statically equivalent tau xy or tau xs is statically equivalent to the vertical load Vs. This means the following: statically equivalent means the resultant of tau x integrated over this section must be equal to df Vy. Resultant moment of tau xy above the concentroid must be equal to the moment of Vi about the same point. That's why d and epsilon z are equal to the moment of tau xy above O, where epsilon z is the eccentricity of the distance Vs from O to avoid twisting. Thus, force Vx is acting instead of Vz is acting instead of Vs. If a force, we determine the shear stress tau xy at any s as putting the Vx equal to 0 and Iz. This is and z axis just opposite. It is positive and this is negative, and this equation remains same. And tau xy Iz qz minus tau Iz qz. Same equation except It is called V and it is called Y. The above stress distribution due to the shear force alone and not due to the twist alone also. Then the moment Vz about the centroid must be equal to the moment of tau xs about the same point itself. So V into epsilon z is the moment of tau x about z. So what is shown? This is Vy, this is the centroid, this is the y-axis, this is z-axis. This stress is theta epsilon z. So this moment from this will be the moment of this shear stress here tau xy about the same weight of O. That only then it will not create an external torsion. And an arbitrary level, V can also be resolved in two components, Vx and Vy and Vz, and the resulting shear stress distribution tau xn at any is given by the superposing this equation 22 and 25 itself. Superposing the point with coordinates Ey and Ez through which Vz and Vy should act to prevent the beam from twisting is called shear center. The point through which the coordinates Ey and Ez through which Vz and Vx is called the act to prevent the beam from twisting is called shear center of the center of flexion. And mentioned in earlier section, it is also shown in this particular section, this point, through which all these things, all these forces acting on anything, which is not may not be on the surface of the section itself, is defined as the shear center of the force itself. Okay. So far, this is our end of our class. Thanks. And I could not tell you clearly because of so many network connections. I'm sorry. So we disrupted internet connection. I'm sorry for that.